xn is less than p, then we talk about the so-called left-sided limit. So xn approaches p from the left here, in this case. Okay, so in the second case, an xn approaches p from the right. Okay, so and these two can be different guys. Okay? Okay, so if you have two, I mean, okay, so let's say the left and the right sided limit are different, then of course the sequence or the function does not converge, because not all, let's say not all sequences will lead to the same limit. That's the point. Okay? So let me just consider an example so where you can see this better. Okay, so let's say that, I mean, maybe you cannot relate to this to anything. So let's say you have f of x, and this is equal to, let's say, this is equal to x plus 1, as, let's say, if x is greater than 1, and it's going to be equal to, let's say, x squared if x is less than 1. Okay? And the function is not defined at point 1. Okay?
Question, maybe a stupid one, but if you have a sequence, let's say, which is described by 1 to the power of n plus 1.
Yes.
Does this converge to 2?
No, as n approaches infinity, this will converge to 0. 1 plus 1 over n converges to 0 as n approaches infinity. Maybe I don't get your point. So
yeah.
So 1 plus 1 over n.
No. 1 to the power of n plus 1.
Okay. So 1 to the power of n.
Yeah. Plus 1.
Plus 1.
It's always 2.
Yes.
Plus, but does it converge to 2?
Yes, it does, because it's always 2. So then we can get,
sure.
In that case.
That's the point, but then this definition of the limit of this function
Yes.
doesn't really work, because it does not approach to.
And so forth, and so on.
You cannot
The distance, I mean, the problem is the distance, okay? So the distance between the limit and the function can get arbitrarily small as x approaches infinity. So as n approaches. But this is actually a sequence. This is not a function.
But in this case, we cannot insert this the members of the sequence in the function because it's always 2.
No, but what is the function here? What is the function?
Function from above.
What? Excuse me.
The function.
I mean, this is enough to denote this as a sequence.
Yes.
I don't need to have a function here.
Yes, but if we go to the example about from above, the function.
But what is the function here?
The function we had earlier. The function.
Which one?
Yeah, this one. X to the power of 2 minus 4 divided by.
So this is a sequence, okay? So x to the power of what? 2 minus 4 divided by x plus 2.
Yes.
And this will be the function. Okay? And then what? And this sequence converges to 2, right?
But it's also always 2, of course.
Yeah.
So
and then what? And then this converges to what?
that's my question, basically.
Yeah, but to what?
But we cannot insert in this function the member of the sequence.
Why not?
Because it's 2 and it doesn't work.
Why does it work? You have 0
sorry.
and
Sorry,
4. So then it's
we have
equal
to
to 0.
we have to construct a sequence which is always minus 2. Then it doesn't work.
And so what? But the limit will be equal to. What was the limit? The limit will be equal to -4 always. The limit is always -4. Always. Doesn't matter.
My point was.
Look, I mean, I understand what you're saying, but the limit is actually -4, no matter what kind of sequence it is. So let me just illustrate the following example. Okay? So your question is, I mean, just have a minute. Okay? So suppose that you have the following sequence, no matter what. So A1 is equal to -2, A2 is equal to -2, A3 is equal to -2, right? Sorry. Or let's call it x, okay? Doesn't matter. You understand? Okay, now the question is, what happens to xn minus 2 squared minus 4 to the power over xn plus 2? What happens to that? That's the point. Now, of course, here the members will not be defined. That's maybe this is what
Always, yes.
what you were talking about. So that's basically a certain point. Okay. In this case, but here we can also actually we can also make the distinction that the sequence never approaches 2, okay? So we can exclude that here because this is a case where all sequences, all members are equal. So if all members are equal, this is a special case that we can exclude here from the definition easily. Okay, but this is just one case where we would do that. Okay, because for all the cases we do. So that's relatively easy to. I mean, I understand the point that in this sense the definition is not consistent, but we can exclude that. So this is something that we would exclude that from the definition. That's relatively easy. Okay, I wanted to make that a little bit more accessible, and basically there is the definition of this. It's a little bit more complicated as you look at the lecture notes. I mean, we have the so-called absent data definition in terms of convergence of the function. So in that case, you would not be able to generate the members of this sequence as you would define. Let's call it Bn. Okay, so if you define this as Bn, then you would not be able to define the members of the sequence, but we would find that the sequence would actually converge, so this is something that might contradict, okay? I understand the point, but this is a good point, but here in this case, I understand, but the thing is this, I mean, we provided, let's say, that the sequence is not equal to a certain number, so that it never approaches, let's say, -2, it's either positive or, I mean, it's greater or less than that, so this is relatively easy to exclude that from the definition. But I didn't do that, of course, and that's a good point. Still, so I didn't do that, but I wanted to make that on the other hand a little bit more accessible. Okay, so basically the definitions are a little bit more complicated than what I was doing here in this case. Okay, so provided that the limit exists and it's well defined. Okay, so in that case, okay, and then you would actually have that result. Okay, so basically, I mean, check it out. So let's go back to the left and the right-sided limit here on this function. So what would be the actual left-sided limit? So maybe you have known the notation, so this is the limit as, let's say, x approaches 1 from the right, okay, so this is the notation. So x approaches 1 from the right, so you have a certain sequence that converges to 1 from the right, always from the right, so it never approaches that, right? So it never is equal to 1, but it tends to 1, so in this case, it tends to 1, so that will be actually the right-sided limit of the function will be equal to what? So the right-sided limit of the function will be equal to 2, obviously, and the left-sided limit, okay, of the function, okay, will be equal to, and will be equal to 1. So this is the right-sided limit, okay? And this is the left-sided limit, okay? Okay? Now guys, since it's 2 not equal, okay, the function does not have a limit at point 1. Okay, so that is actually something that we have to consider. Okay, so the function itself does not have a limit at point 1, because in that case, the limits for all actually here, so this will be for all, okay, so for all sequences must be equal, and this is not the case. Okay, so for all sequences that converges to -2, the limit of the function is equal to -2 always. So the function always tends to -4 as a sequence tends to -2, and this is always the case, no matter where the sequence is coming from. You understand that? Okay, but here, actually, in this case, the limit of the function f of x as x approaches does not exist. Okay? So only the left and the right side limit of the function exists. You get that, guys? Okay? So no more. That's it. Okay? Okay? You get that? Okay? You seem to be like a little confused. Okay? So only the left and the right side limit exists. Okay? And both are different. So, but here in this case, I mean, let me just make the following statement. So, if a real valued function, okay, so for a real valued function of real variables, there are only actually two directions from which you can approach a certain number, either from the left or from the right, okay? and if you're doing this like that. Okay, so for real valued function of real variables, the limit exists. The limit of the function at a certain point exists if and only if the right and the left-sided limits are equal and both are finite. Okay, so let me make the statement here. So this is len of 5.21. Okay, so the limit of a real valued function, the limit of a real valued function of real variables. So what does that mean? Real valued function of real variables. Remember that? So that means that all arguments are real numbers and all results, or so that's all images are also real numbers. Okay, so this is a real valued function of real variables. Exists as x approaches p, if and only if the right and the limit exists. Okay, the right and the left-sided limits, or the right and left-sided limits of the function exist, okay, and are equal. Okay, and of course it must be finite as well. Okay, so by meaning if they exist, so this is that actually. Okay, that it means that it also has to be finite. Okay, so if it's infinity, then the limit does not exist. Okay, so here in this case, okay, the right-sided and the left-sided limit exists. Okay, but they are not equal. Okay, so since they are not equal, all right, then the limit of the function does not exist. Okay, you understand? Okay, so here this is less than infinity, and this is also less than infinity, so that these limits exist. Okay, but they're not equal, so therefore the limit of the function does not exist at that point. Okay, you understand that? Okay. All right, guys. Now we're going to talk about continuity. Okay, so this will be the next definition, and I will talk about it later on. So this will be the next definition. So this is continuity of a function. Of a function f of x at point P. Okay, so a function is supposed to be continuous at a certain point P if the following statement is true. Okay, so if let's say you have a sequence that converges to P, so if a sequence converges to P, then this must imply that the image of the sequence, okay, must also converge to the image of P. You understand? So this is what continuity means. Okay, as a sequence progresses. I mean, here in this case, the limit of the function can be also different than actually the image of the limit as a sequence converges to P. Okay, but if that statement is true, then the function is called continuous. Okay, all right. So if x converges to P, then the image of the function, or the image of x, or the sequence, or image of the sequence, or the members of the sequence, must also converge to the image of the limit P, which is P. P is the limit of the sequence in that case. So in this case, the function is called continuous. Okay, so continuous at point P to be precise. All right. Now, and there is also left and right-sided continuity. Okay, so the left continuous and right continuous, or right continuity of the function, and the left continuity function. But you understand that point. Okay, so as x approaches P, this must imply that f of x, and okay, so x is a sequence, approaches f of p, and let's say for all sequences. Okay, so that is why the definition is a little bit more, it's easier to understand, but it's more complicated because, I mean, we would check actually for all sequences. Okay, so that could be the property. All right, you understand? Okay, so for instance, I mean, you can check it out. So here, for instance, this function's here. Let's say, I mean, look at that function, and you have here the point p. Okay, so this function is continuous at point p. This is the image of p here. You can see this. Okay, so here you have the image of p. Okay, and any sequence. All right, and any sequence. Let's say you have a sequence xn. Any sequence that approaches p will have the consequence that, let's say, the image of that is here. So this will be f of xn. All right. So you find this here, and that is something that you obviously see. Let me just demonstrate this again. Okay. So here you have, let's say, a sequence xn somewhere. Okay. And that approaches, the sequence approaches p here, let's say, from the right. Okay. In this example, but it could be also from the left. So now that would be, the consequence of that would be that actually the image of the sequence here would also approach the image at point, the image of p. So here in this case, you can say that the function is continuous at point p. Okay, so this is what you have here. So f of x is continuous at, okay, at point p. Okay, you understand? Okay. This is what we were talking about. Okay, so the distances can get arbitrarily small. Okay, so here in this case, I mean, this is a extremely simplified definition, of course, guys. Okay, but here you would also find that this will be also the case as well. Okay, all right, guys. I apologize. I have to hurry. Okay, so I'm not able to answer your questions after lecture today. I apologize for that because I missed the class. Missed the second class. I'm not supposed to do that. Okay, but if you have questions, I'm very happy to answer them after Friday. Okay, so Friday after the second lecture class. Okay, I apologize. Okay, we'll see you on Friday, guys. And please do not forget your assignments. Right? Okay. Assignment number 4.